Swayam Prabha. Digital India. Educated India.
Hello, we will continue our discussions on kinetics of particles, and in this lecture I am going to show you how our approach can be used to understand certain natural phenomena. We will apply the Newtonian dynamics, laws of motion, and look at some problems, and based on this problem that I am going to discuss, I will show you a natural phenomena that is based on this, or that can be understood from this problem. This says a freshly painted cylinder, a small cylinder, initially held stationary on the edge of a frictionless uniformly rotating disc of radius r is projected radially inwards, that means towards the center, with speed u relative to the disc. This you should notice carefully, that this speed is given, or the velocity is given relative to the disc. The part A tells you to set up the equations of motion of the cylinder for an observer on the disc. So, this observer is rotating with the disc. And B, determine the path of the paint mark left on the disc, assuming that the rotation speed is small. First step is to set up the coordinate system. I am going to use the Cartesian coordinate system, which I will fix to the disc. This xy coordinate system, xyz coordinate system is fixed to the disc. The disc is rotating in a counterclockwise direction as seen from the top. And for simplicity, just for simplicity, I am considering that this particle P, or the cylinder P, was initially in the negative y axis direction as shown here, and projected along the positive y axis direction towards the center. So, this is our coordinate system, then the free body diagram, the weight of the disc and normal reaction. These are the only two forces acting on the cylinder. There is no friction in this case. Now, the kinematics. The velocity of the cylinder as observed by an inertial observer is equal to the velocity as observed by the disc fixed observer at O plus Vrel, the relative velocity as seen by the observer in his or her frame, plus omega cross OP vector. Now, this is the expression of velocity we have studied before, and this OP vector is the vector from O to the particle at any location. Suppose when the particle or the cylinder reaches here, then OP vector will be this, and everything has to be represented in this xy coordinate system, and that is what we are going to do now. Acceleration of this particle, therefore, first I have written out the most general expression. Acceleration of P is acceleration of O plus ARel plus alpha cross OP plus omega cross OP plus 2 omega cross Vrel, of which you will notice that the absolute acceleration of the observer who is sitting at the origin and on the axis of rotation, therefore, is 0, the acceleration is 0. Alpha, the angular acceleration of the disc, is 0. We are assuming that it is rotating at a constant angular velocity. Now, I represent the relative velocity etc. as measured by this disc based observer who is using this xy coordinate system. The vector OP, let us start with this vector OP, nothing but xi cap plus yj cap. This is as seen by the observer on the disc. Vrel, this is as measured by the observer, this is not the absolute velocity of the particle, remember, it is the velocity as measured by the observer in the rotating frame, that is x dot I cap plus y dot j cap. ARL similarly is x double dot I cap plus y double dot j cap, and omega vector represented in this x y z coordinate system is omega k cap. Therefore, plugging in these expressions, I find the expressions of velocity, which I have here. These are along I cap and j cap directions, and acceleration, which simplifies. I have done some simplifications, and this is the final expression of acceleration. This is the velocity and acceleration. Now, the kinematics is set, we will move to the equation of motion. Mass times acceleration of the particle is equal to the net force acting on the particle, which is simply the weight and the normal reaction. Now, look at the components. The I cap component, j cap component and k cap component. This is the I cap component, this is the j cap component, and this is the k cap component. Since there is no acceleration in the k cap direction, it is only balance of force. What it tells us is the normal reaction is equal to the weight. Now, we have these two equations, dynamical equations, which will tell me how the particle is moving on the disk. So, these are our relevant equations, and there are two second order ordinary differential equations. We will need these initial conditions, 4 initial conditions. So, at time t equal to 0, it starts at x equal to 0 and y as minus r, and its x velocity was 0 and y velocity was u, and remember this is relative to the disk. So, y dot is actually relative to the disk. So, that is equal to u. Now, we solve these equations, relevant equations of x and y. These are two ordinary linear second order differential equations, they can be solved exactly. This can be solved exactly, but what we are going to do is, rather than trying to solve it exactly and get a very complicated solution, it is a little lengthy solution, but you can try out. We are going to make some approximation, and this approximation will be relevant to the next part of the discussion in this lecture. We will assume that this omega is small, so that omega square can be dropped. I will drop omega square from these two equations. In that case, my equations slightly get simplified, and as shown here. So, these are our equations under the assumption that omega is small, so that we can drop omega square. Now, I can start integrating these equations and use the initial conditions that we have discussed. If you integrate the first equation, you will get, and use the initial condition, then you will get x dot minus 2 omega y is 2 omega r, and the second equation gives us omega dot plus 2 omega x equal to u, and you can check that this satisfies all the initial conditions. Now, I substitute back these expressions of x dot and y dot in these equations. So, what I do is these two expressions I substitute back y dot and x dot. If you substitute back, then you will get these two equations. Again I will drop omega square. If I drop omega square once again, then the first equation gives me x double dot minus 2 omega u is equal to 0, it is constant therefore, and y double dot is 0. So, approximately 0. So, these are our simplified equations. Now, they are really simplified, and I can again use these initial conditions and integrate. Straightforward integration, x double dot is constant, y double dot is 0. So, these are the integrals, and now you will notice at time t equal to 0, x equal to 0 and y is equal to minus r as the initial conditions demand. if I eliminate time between the two, how I will eliminate? I will solve time from the first equation and substitute in the second. I will get the equation of the path, and this shows that y changes as square root of x. In other words, there is a parabolic relationship. You should first notice that as time progresses, x increases and y initially reduces, because it starts from minus r, or rather it increases in a way. So, y increases like this, and this, therefore, because x moves to positive side, the particle path curves to the right, it curves to the right, and you can write this as y plus r whole square omega by u as x. This is a parabolic relationship between x and y, only thing the parabola is like this. This is the parabola, it is only shifted in the y axis by a distance r. Therefore, this is the path of the paint mark, because remember x and y are coordinates as measured by a frame or from a frame which is fixed to the disc, and this path is therefore on the disc. The paint mark will be on this approximately parabolic path. Remember, we have done some simplifications. Notice the first point is that the particle turns to the right. What happens if omega is reversed? If I take omega in the clockwise sense, which means I change the sign of omega here, the particle will curve or veer to the left. The change of y remains the same. Y does not involve omega here in the approximate solution. Therefore, this particle is going to curve to the left if omega direction is changed. So, if it is a counterclockwise rotation as seen from the top, the particle will veer to the right. If it is clockwise, it will veer to the left, just opposite. Second thing, you observe that this feature will not depend on where you had started the particle from. By that I mean that if you had, instead of taking that simplifying assumption I started with, that it is on the y axis in the negative r, if I had started the particle from here, this observation would have remained the same, it would have curved to the right with the counterclockwise rotation, and this is what I have drawn here. If you start the particle from various sides radially inwards, they will all curve to the right, and if they all curve to the right, this is suggestive of something, and if you are thinking about cyclones, we are going to get there next. But to understand cyclonic circulation, we must first consider Earth as a rotating frame. I have here shown the calculation of what is the omega of the Earth. It rotates 2 pi radians in 24 hours, that is 24 times 3600 seconds, and the omega of Earth turns out to be 7.27 into 10 to the power minus 5 radian per second. It is a very small angular velocity, I am sure you will agree, but this small angular velocity can create havoc. As you know, it can damage buildings, it can break houses and uproot huge trees and do what not. This small angular velocity. Therefore, the effect of Earth's rotation can be grand, even though in many situations we do neglect it. Okay, let us now look at a point on the surface of the earth at a latitude phi. I indicate this angle in the figure. You see the phi, that angle phi is measured from the equator. This red circle is the equator, and as you know, latitudes are measured from the equator. Equator being 0, it moves up to 90 degree for the north pole, minus 90 degree to the south pole. I consider a plane which is tangent to the point, that point which is under consideration. That point on the surface of the earth at a latitude phi, I take a tangent plane, tangent to the earth. I fix up a coordinate system like this, that in the east direction I have x axis, towards the north at that place is the y axis, and z axis is vertically upwards from the center. Now, the omega of the earth, that vector, can be represented in this coordinate system, and if you do, it is a vertical, I mean in the figure it is vertical, and at a latitude phi, vertical line. So, this angle must be phi, this angle is phi. Therefore, about the z axis is its omega e sin phi, it should be phi, omega e sin phi. And there is another component about the y axis which will be omega e cos phi. Now, this omega e sin phi is similar to the omega of the disk problem that we have discussed. This omega is along the axis of that disk, or in this case the plane. Now, imagine that you have developed a low pressure region at that location which is under consideration. Suppose there is a low pressure region at that location. This happens because hot spots develop and hot air is lighter, it rises up and the pressure drops at that location. Therefore, air from the surrounding regions, they rush in towards that low pressure center, and once they rush in, it is same as our cylinder being projected radially inwards on a rotating disc. Why rotating disc? Because here also the plane is rotating and its angular speed is omega e sin phi. Therefore, these particles will curve to the right, it is counterclockwise as seen from the top, the rotation is counterclockwise as seen from the top in the northern hemisphere. If phi is positive, this by the way is phi in the northern hemisphere is positive, therefore, this angular velocity is counterclockwise as seen from the top, therefore, the particles, air particles will veer to the right, it will, and starting from every location it will veer to the right, and that starts the cyclonic circulation, this starts the circulation. Therefore, in the northern hemisphere where phi is positive, you have a counterclockwise rotating circulation. Now, this is the image of the Amphan cyclone, super cyclone. Northern hemisphere, it is off the coast of Tamil Nadu in the Bay of Bengal. The source is from the Indian Meteorological Department, and I have marked the direction of circulation, it is counterclockwise. This is in the northern hemisphere. If you look at southern hemisphere, this is the super cyclone Katarina which hit the coast of Brazil, this part is Brazil. And you can clearly notice here the cyclonic circulation direction is just the opposite, and the equator passes somewhere here. north of Brazil. This is about 10 degrees south, and here the circulation is clockwise. Thus, our discussions has led us to this understanding of cyclonic circulation. So, to summarize, we have looked at kinetics of particles and applied Newtonian dynamics to understand cyclonic circulation, and with that I will close this lecture.